Hello everyone. Today we are going to analyze this beam using flexibility matrix method. In this analysis, we are going to take the vertical reactions in the points B and C as redundant. Now let us see the beam one time. In this beam, there are two spans, span AB and span BC. In the span AB, there is an eccentric point load 45 kN. It is acting at a distance of 2 meter from the point A. In the span BC, we have uniformly distributed load 15 kN per meter acting for the full span. The moment of inertia for the span AB is 1.5 I. For the span BC is 2I. Length of AB is 6 meter. Length of BC is 4 meter. In the point A, there is a fixed support. In the points B and C, there are hinged supports. Now let us find the degree of static indeterminacy. In this beam, the number of unknown reactions and moments is 4. They are MA, RA, RB and RC. The available equilibrium equations are 2. Sigma m is 0 and sigma v is 0. The degree of static indeterminacy is 4 minus 2. We will get 2. Let us release RB and RC. When we release them, this continuous beam becomes a cantilever beam. This beam is called the released structure. I have analyzed this very same beam by taking MA and MB as redundant. You can see the link for the video in the description. We have made the released structure. Now let us make the coordinates diagram. In this analysis, there are two coordinates. We have the coordinates in the points B and C. Because in these points only, we have removed the vertical supports. Now let us see the formula to find the reactions RB and RC. P matrix is equal to delta matrix inverse into delta matrix minus delta L matrix. Inside the P matrix, we will have RB and RC because these are the reactions we have removed. Inside the delta L matrix and the delta matrix, we will have two values because in this analysis there are two coordinates. The size of the delta matrix will be 2 cross 2 since the coordinates are 2. In the given beam, there will be no final displacements. So inside the delta matrix, we can simply enter 0, 0. If there is settlement or sinking of the supports in the beam, there will be values. Otherwise, we can simply enter 0. So in this formula, only we have to find delta L matrix and the delta matrix. To find the displacements and make the matrices, we are going to use unit load method. In this method, we have to find the moment caps m. Using the loads given in the question, we can find the moment m. Then we have to find the moment m1. For that, we have to apply the unit load in the first coordinate. Our first coordinate is in the point B, so I have applied unit load in the point B. Then we can find the moment. To find the moment m2, we have to apply unit load in the second coordinate. Our second coordinate is in the point C. So in the point C, I have applied unit load. We have to be very careful. When we find m1 and m2, we should remove all of the loads. To find the moments m1 and m2, we have to make sections in this beam. In this beam, there are three different parts: AD, DB, and BC. So we have to make three sections, one in AD, one in DB, and one in BC. You can see that I have made three sections. The first section in BC, the second section in DB, and the third section in AD. Before finding the moments, let us make the free body diagram so that we can easily find the moments. For making the free body diagram, I am going to split the beam in the point B. First, let us take the right side portion of the point B. Due to this load, a reaction is created in the point B. To find the reaction, we have to find the total load. Here there is UDL. To find the total load, we have to multiply the UDL with the distance. When we do that, we are getting 60. Since the UDL is acting downwards, the reaction should be acting upwards. Now let us find the moment in the point B. For that we have to multiply the UDL with the distance and distance by 2. When we do that, we are getting 120. Since the UDL is acting in the clockwise direction, the moment developed should be acting in the anti-clockwise direction. Now let us take the portion on the left of B. On the right side in the point B, we have a vertical reaction 60 acting upwards. So on the left side, it should be acting downwards. On the right side, we have a movement which is acting in the anti-clockwise direction. So on the left side, it should be acting in the clockwise direction. Now let us find the vertical reaction in the point A. Here there are two loads. We have to add them. After adding, we are getting 105. Since these loads are acting downwards, the reaction should be acting upwards. Now let us find the moment in the point A. In the point B, we have a clockwise movement 120. This point load is acting in the clockwise direction and the distance is 6. This point load is also acting in the clockwise direction and the distance is 2. So 45 into 2. When we add all of them, we will get 570. Since the movement and the loads are acting in the clockwise direction, this movement should be acting in the anti-clockwise direction. Now let us take BC and find M. We have made the first section in BC. I have made the section at a distance of x from the point C. For member CB, the moment of inertia is 2I. So the flexural rigidity should be 2EI. The origin of the section is in the point C. The limits are 0 to 4. Now let us find the moment M. We are going to find the moment from the point C. In this case, we are moving towards left-hand direction. Clockwise will be negative and anti-clockwise will be positive. Up to the section, we have only one load, that is the uniformly distributed load 15. The UDL is acting towards the section in the clockwise direction, so it will be negative. For the UDL, we have to multiply the distance and distance by 2. Here the distance is x, so x into x by 2. 15 upon 2, we will get 7.5. So the moment is minus 7.5 x square. Now let us take the portion BA. In BA, we have made two sections. The second section in BD and the third section in DA. First, let us take the second section. I have made this section at a distance of x from the point B. For BD, the moment of inertia is 1.5i, so the flexural rigidity should be 1.5 EI. The origin of the section is in the point B. The limits of the section is 0 to 4. Now let us find the moment. Up to the section, we have the load 60 and the moment 120. The load is acting in the clockwise direction, so it will be negative and the distance is x, so minus 60x. The moment is acting in the clockwise direction, so it is also negative. Now let us take the third section. I have made this section at a distance of x from the point A. If you want, you can make this section from the point B also. But when you do that, you should select the limits as 4 to 6. For me, it is convenient from the point A. So I have made the section from the point A at a distance of x. The moment of inertia for the span AB is 1.5i. So for AD, the flexural rigidity is 1.5 EI. The origin of the section is the point A. The limit is 0 to 2. Now let us find the moment in this section from the point A. In this case, I am moving towards right hand side. Clockwise will be positive and anti-clockwise will be negative. The reaction 105 is acting in the clockwise direction, so it will be positive and the distance is x, so 105x. The moment is acting in the anti-clockwise direction, so it will be negative. We have found the moment using the given loads. Now let us find M1. For that, we have to remove all the given loads and apply unit load in the first coordinate. Now let us make the free body diagram. Let us assume that the unit load is applied just left of B, so no need to consider the right side. Due to this unit load, a reaction is created in the point A. This load is acting upwards, so the reaction should be acting downwards. Now let us find the moment in the point A. This load is acting towards the point A in the anti-clockwise direction and the distance is 6. So 1 into 6 we will get 6. Since this load is acting in the anti-clockwise direction, the moment developed should be acting in the clockwise direction. Now let us find M1 in the first section. Up to the first section, there is no load, so the moment will be 0. Now let us find the moment in the second section. This unit load is acting in the anti-clockwise direction, So it will be positive and the distance is x. 1 into x, we will get x. Now let us find the moment in the third section. This load is acting towards the section in the anti-clockwise direction. So it will be negative and the distance is x. So we will get minus x. This movement is acting in the clockwise direction. So it will be positive. Now we are going to find M2. To find M2 in the second coordinate, we have to apply unit load. You can see that I have applied unit load in the second coordinate. Because of this load, a reaction is created in the point B. It is acting upwards, so the reaction should be acting downwards. Now let us find the moment in the point B. This load is acting in the anti-clockwise direction and the distance is 4. 1 into 4 we will get 4. Since this load is acting in the anti-clockwise direction, the moment developed should be acting in the clockwise direction. In the point B, in the right side, the unit load is acting downwards. So on the left side, it should be acting upwards. On the right side, the movement is acting in the clockwise direction. So on the left side, it should be acting in the anti-clockwise direction. Due to this unit load, a reaction is developed in the point A. This load is acting upwards, so here it should be acting downwards. Now let us find the moment in the point A. This load is acting in the anti-clockwise direction and the distance is 6 meter. So 1 into 6. This movement is also acting in the anti-clockwise direction. After adding, we are getting 10. Since the load and the movement is acting in the anti-clockwise direction, the developed movement in the point A should be acting in the clockwise direction. Now let us find M2 in the first section. This load is acting towards the section in the anti-clockwise direction, so it will be positive and the distance is x. 1 into x, we will get x. Now let us find M2 in the second section. This load is acting in the anti-clockwise direction, so it will be positive and the distance is x. 1 into x, we will get x. The movement is also acting in the anti-clockwise direction, so it is also positive. Now let us find the movement in the third section. The unit load is acting in the anti-clockwise direction, so it will be negative and the distance is x, so minus x. The moment is acting in the clockwise direction, so it will be positive. Now let us make delta L matrix. In the matrix, first let us find delta 1L. The formula is integration of m1 upon ei dx. Let us take the portion CB. When we multiply m into m1, we will get 0. So no need to make the integration. Now let us take the portion BD. For BD, the flexural rigidity is 1.5 EI. So instead of EI, we have to apply 1.5 EI. The limits are 0 to 4. Then let us apply the values of m and m1. Now let us take the portion AD. For AD also, the flexural rigidity is 1.5 EI. So in the formula, instead of EI, we have to apply 1.5 EI. The limits are 0 to 2. Then let us apply the values of m and m1. Then we can use the calculator and do the integrations. If you do not know how to use the calculator for making integrations, see the description below. There is a link. You can click the link and watch the video. I have used the calculator and got the values. After adding these two values, I am getting delta 1L. Now let us find delta 2L. The formula is integration of m2 upon EI dx. For CB, the flexural rigidity is 2EI. So instead of EI, we have to apply 2EI. The limits are 0 to 4. Let us apply the values in CB, then BD, then in AD. Then we can make the integrations, and then we have to add these three values. After adding, we are getting delta 2L. In delta L matrix, we have found both of the values. Let us apply them. 1 upon EI is constant. Let us keep it outside. Now we are going to find delta matrix. First, let us find delta 1 1. The formula is integration of m1 square upon EI dx. For CB, the value of m1 is 0, so no need to make the integration. Let us apply the values of m1 from BD and AD. After making integrations, we are getting this. Then after adding these two values, we are getting delta 1 1. In this matrix, now let us find delta 1 2 and delta 2 1, both of them having the same formula, integration of m1 m2 upon EI dx. In CB, for m1 we have 0, so no need to make the integration. In BD, let us apply the values of m1 and m2, and then in AD, let us apply the values of m1 and m2. Finally, for delta 1 2 and delta 2 1, we are getting 96 upon EI. Now let us find delta 2 2. The formula is integration of m2 square upon EI dx. In the integration, let us apply the values of m2. Finally, we are getting delta 2 2. In the delta matrix, we have found all of the values. Let us apply them. 1 upon EA is constant. Let us keep it outside. In this formula, we have found everything. Let us apply them. 1 upon EA inverse is EI. For this matrix, we have to find the inverse. We can apply all of the values in the calculator and get the inverse. If you do not know how to find inverse in the calculator, see the description below. There is a link. You can click the link and watch the video. I have used the calculator and got the inverse. We have to add these two matrices. After adding, we are getting this. Then we can eliminate this EI and this EI. Then we have to multiply these two matrices. After multiplying, we are getting RB and RC. For RB, we are getting 48.67 kilonewton. For RC, we are getting 24 kilonewton. Now let us apply the rule. Sigma V is 0 and find out RA. RA, RB and RC are acting upwards, so all three of them will be positive. The point load 45 kN and the UDL 15 kN per meter are acting downwards, so both of them will be negative. Finally, we are getting RA, which is equal to 32.33 kN. Then from the point C, we can find the moment in the point B. In this way, we can find MB. Then from the point C, we can find the moment in the point A. In this way, we can get MA. For MA, we are getting minus 38 kilonewton meter, and for MB, we are getting minus 24 kilonewton meter. Now let us make the shear force diagram. Before drawing the shear force diagram, let us calculate the shear force values. I am calculating the shear force values from the point A towards the point C. In this case, I am moving towards right hand side. Upward forces will be positive and downward forces will be negative. You can see the calculations here. Now let us make the shear force diagram. For the positive values, we have to draw the diagram above this line, and for the negative values, we have to draw below the line, and we have to mark as positive and negative. Now we are going to draw the bending moment diagram. For the bending moment diagram, first we have to make the free moment diagram and end moment diagram, and then combine both of them to get the bending moment diagram. For the free moment diagram, we have to consider each span a separate simply supported beam. We have already calculated the ordinates. For the span AB, it is 60, and for the span BC, it is 30. Using the ordinates, we can make the free moment diagram. Using the end moments, we can make the end moment diagram. In the point A, we are having a moment MA 38. In the point B, we are having MB 24. And in the point C, the moment is 0. If the end moment is negative, we have to mark the points above the line. If it is positive, we have to mark them below the line. In our case, both of the moments are negative. That is why we are marking them above the line. Now we can combine the free moment diagram and end moment diagram. Wherever they are alone, we are marking the values with the sign. Here the end moment diagram, here the free moment diagram, end moment diagram, and free moment diagram. Wherever they are together, we are not marking. We are just keeping the space empty. If you are very experienced, no need to make the free moment diagram and end moment diagram. We can directly draw the bending moment diagram, so we can save a lot of time. Now we are going to end this session. Thank you for watching this video.